Hello friend, in this lecture we are going to look at the resistor inductor series DC transient. Now let us look at this drawing of ours with an inductor with the voltage VL, resistor with the voltage VR, with a switch closed here and the voltage source resulting into the flow of current I. The total voltage, therefore, V is given by Kirchhoff's voltage law and is equivalent to V equal to VR plus VL. We know that voltage drop across a resistor is IR. What about VL? We know that VL, the voltage developed across an inductor is due to the induced voltage or induced back EMF, which is given by L di dt. Therefore, we know that across an inductor there is a changing current. So for an inductor, current changes with time, and hence VL is equal to L di dt. Now, if we are substituting in our values of VR and the VL, we realize that V is equal to IR plus L di dt, and V minus therefore IR divided by L, or the inductance of the inductor, is equal to di dt. Therefore, reorganizing this formula so that we can have the right terms together, we put the constants this side, we integrate with respect to I this side, and integrate with respect to time on this side. It means we shall have L over R over L dt, integral of L over R with respect to time, and the integral of 1 over V out of R minus I di dt. I mean integral of 1 over V over R minus I with respect to I, which is current. What does this give us? It means if we integrate that, we shall introduce a constant of integration this side, so it becomes k plus r over L times t equaling to negative natural logarithm of V out of R minus I. Because when we integrate, for example, when the integral of 1 out of V out of R minus I with respect to I would give you the negative natural logarithm of V out of R minus I plus a constant. Therefore, if we remove the natural logarithm this side, it will be V out of R minus I equaling to exponential of negative RT divided by L minus K. So when we introduce the same base with the different powers, of course, if we have something like this, it means we have a multiplication of the bases. So E of negative K times E of negative R out of L times T is equal to V out of R minus I. But because the exponential of negative K is a constant, we can let it to be a constant as say K1. What about when we substitute it in our formula? It therefore means that I is equal to V out of R minus K1 exponential of negative R out of L times T. So when we apply the boundary conditions or the initial conditions, it means that T is equal to 0, current through the inductor is equal to 0 because of the inductor's action. The inductor is that device actually that always hates the change in current. Any change in current, the inductor will try to stop it. Therefore, at the instant when the switch is closed at T is equal to 0, the current flowing through the circuit will be 0 due to the inductor's action. Therefore, when we substitute in this formula, it means 0 is equal to V out of R minus K1 exponential of 0 because of this value. It will give you V out of R equal to K1. So substituting in it in the above formula, it gives us the fact that the current flowing through the circuit will be V out of R minus V out of R exponential of negative R out of L times T. And therefore, when we rewrite that one properly, factorize out V out of R out of the brackets, it will be 1 minus exponential negative R out of L T. And when we plot these values, we realize there is an exponential growth of current. This is the transient. This is the transient period, beyond which we attain the steady state of these values. Actually, here, now that is current, after the transient period, there is attainment of the steady state values. Now, this is the graph, of course, shown as above. This is the steady state, this is the transient period, and our current through the circuit is that one. So if tau is equal to R, L out of R, and is called the time constant, we can define it as the time taken for a transient to reach final state if the initial rate is maintained. Or it can also be the measure of the rate of a transient parameter, the rate a transient parameter builds up to its steady state value. Usually the steady state conditions are attained after 5 time constants, which is always equivalent to 99% of the steady value. Therefore, our I of t, or the current as a function of time across a circuit that has a resistor and an inductor, will be V out of R into 1 minus exponential of negative t divided by tau, which is the time constant. What about the voltage across the resistor? The voltage across the resistor is also the voltage drop is also increasing up to a steady state value of VR equal to V. So VR is equal to IR. We know the formula for current already. We substitute it in, we multiply by R, and therefore the voltage drop across the resistor will be VR equal to V into 1 minus E exponential of negative t divided by tau, and which shows you an exponential growth of voltage across the resistor. What about voltage on the inductor? Having the fact that voltage on the inductor is the induced EMF, it means VL is equal to L di dt. When we substitute in our value for I, it will be VL equal to L times D of V out of R, which is the value for I, into 1 minus exponential of negative t divided by tau with respect to time. So when we differentiate that value, we realize that it will be L divided by R times, it is actually negative L divided by R times R out of L into negative V exponential of negative t divided by tau, which will be V exponential negative t, because this and that will go and that will go, and will remain with a negative. This negative here will die with that negative. Therefore, voltage build up across an inductor is an exponential voltage decaying, which is V exponential negative t divided by tau. And we can see it from this graph of ours that there is a voltage exponential voltage decay with a maximum at V, and which decays with as time goes by. As time approaches infinity, this voltage across the inductor will become 0, and therefore at t equal to infinity, the inductor behaves as a short circuit. Thank you so much for watching.